Hi, I'm Glenn. I am a postdoctoral associate in the Robot Locomotion group, working with Professor Russ Tedrick. So I'm interested in how we can get robots out into the real world and to have them have kind of guarantees on safety and reliability, even when completing really complicated tasks of human complexity, for instance, like cooking or driving or performing surgery. Yeah, so in recent years, these machine learning methods have really provided really impressive results on a lot of robotics tasks, but a key shortcoming of all these methods is still that they are quite unreliable. And this has been catastrophic, for instance, in applications like autonomous driving. And really, ultimately, we're going to need to think about safety kind of more carefully if we want to apply these kinds of methods, these kinds of robots around humans. And so yeah, one thing that you need to really think about is whether or not we can ever really collect, for these purely data-driven methods, can we really ever collect enough high-quality data in order to, can we ever really collect enough high-quality data in order to reach 3, 4, 5 nines of reliability? And this is a problem even in kind of situations where human lives are not directly at risk. You can imagine, are you going to really want to buy a robot dishwasher that is going to break every 100th dish, for instance, like that? So to me, a promising way forward is to blend the traditional tools of model-based control, which have these reliability guarantees, with these more recent data-driven approaches to control, so that we can be flexible to uncertainties in the environment. In particular, one thing I'm interested in doing is how we can get these guarantees when our robots are operating off of high-dimensional observations, like RGB images, like depth images, which are kind of the sensing modalities that we're actually going to be able to realistically obtain in the real world. How we can do that with model-based tools. So you'll see a drone flying around in a kind of simulated environment, and in particular, the drone does not actually observe fully its state. It's only going to get information about where it is from a camera that's been attached to onboard on the quadrotor. And this is, in general, a pretty challenging problem because there's partial observation. It's not going to uniquely define what the quadrotor's state is from the single image. So our controller is going to have to be able to reason about kind of sequences or histories of images that the robot has seen in order to successfully stabilize from some start state to some goal state. So for instance, when we were trying to come up with these stabilizing controllers for this quadrotor system, stabilizing from these camera images, it turns out that actually very simple controllers could provably stabilize these systems with very large regions of attraction, meaning these controllers basically work reliably in a very large part of the robot state space. And that's kind of surprising in the sense that right now all the controllers that are being deployed on all these learning-based controllers basically are very complicated. They're all these very large neural networks. And it turns out that, at least for these kinds of settings, if it turns out that we can actually do reliable control with just a controller that, in this instance, for instance, only had less than 10 parameters or something like this, if we can get very simple controllers to perform complex behaviors, then this can actually be useful later down the line. It can make these controllers easier to verify, more explainable, and that can be kind of important down the line, I would say. Yeah, so I think moving forward, what I'm really interested in is whether or not we can apply these model-based techniques and really scale them up to much more complicated tasks, like for instance, some kind of contact-rich manipulation task, and how we can do that from these high-dimensional observations, like images, like RGB images, things like this, with these kind of guarantees of safety and of reliability that our model-based approaches can provide us. And yeah, I think one of the challenges in doing this is going to be how you can reason in a scalable fashion about the complex dynamics of contact. This basically gives you hybrid dynamics that makes synthesizing these model-based controllers much more challenging, but this is, we're looking into this and seeing if there is a way to make this more scalable. Yeah, we have a paper that will be linked in the description on our work on perception-based control with guarantees. And if you're interested, please go and take a look. So thank you.